Just like the ocean.
That was for the HOA places.
And even that's not for certain.
Okay, so tonight, what we're going to talk about is antennas. And these are dipole antennas and vertical antennas. And what I hope for, what my goal for you guys tonight is to make you all comfortable with the idea of building your own or putting your own antenna up. And even if you purchase an antenna, you'll know kind of behind the theory behind what they do, how they work. So they're not quite so mysterious. I know some of you may not have, they may not be such a mystery anymore, but when I first started, it was like magic, you know. It might be still magic, but we'll see. And how is it that Norm Abram want to take a moment and talk about safety? You know, the obvious things, wearing your safety glasses. Something a little not obvious is there are a lot of homes, especially in residential neighborhoods. I think you guys, Jeff, you don't have power lines so close, but the primary lines that feed into neighborhoods, to feed houses in Springfield, vary from 4,500 volts to 12,600 volts. They're capable of about an amp and a half of current, which means they will kill you in a millisecond. And it sounds harsh, but to be honest with you, I was a pallbearer at a funeral for a guy that was putting up CB antenna, and they could not make him look nice for his money. So watch where you put the antenna. If you're putting up a metal pole, it has to be as far away from the power lines at the base as the whole thing is tall. That way, if it falls, it's not going to come anywhere near. And so be very careful. Watch out where you're putting wires. If you got your brand new pneumatic antenna launcher and you're going to shoot a line over a tree, make sure there's not a power line on the other side of it. There's tons of videos about electrical safety, but do be careful. You don't want to lose anybody just because they put an antenna up.
And Steve, if I could add one thing to that real quick. In addition to those big lines, you got to be careful of your service line that's actually coming from your pole to your weatherhead. Because like in a situation like I had at my house that I just sold, it actually went diagonally across the middle of my backyard. It didn't go at one end or the other, so kind of be mindful of those because they apply.
Well, those are insulated.
But you can
Still be careful.
You still need to be careful. I'm not
Treat them
saying
like
that.
they're live lines.
Yeah, but they are insulated, so.
So, what we're going to talk about, there was a guy named Heinrich Hertz, and he was the first one to come up with the idea that energy can go into a wire and actually leave it through the air. Marconi kind of followed it up with another variation on the Hertzian antenna. We're going to talk about how you get energy into it, what it means to have SWR or VSWR, and then stuff that you can build. This seems a little bit like a long time ago, doesn't it? 1887. I mean, that wasn't that far past Civil War, and this guy figured it out. And honestly, guys, I've heard people say, "Well, I can't work on electronics. I don't have any test equipment." I don't think Hertz did.
He invented the test equipment.
I think so. Yeah. So, the dipole antenna, which is basically a wire with an insulator at each end and a feed point somewhere along the way. That's what he came up with. This is probably, for anyone who's built an antenna for yourselves, this will be the first one. It's the easiest one to build. I've got one right here, as a matter of fact. And anybody who knows me will know what the green things on the end are. Yeah, soda pop.
From Mountain Dew, I believe.
Mountain Dew.
Yeah.
So this is an antenna roughly for 6 meters. And I didn't actually measure it because I got an arm span of about 6 feet and I added 30. And usually they come out. So simple, basic, the phone wire, the phone guys, they work on the little box out the front, and occasionally they leave me a gift, and that's the 500-foot long twisted pair phone line that's what they do. So, you guys are interested. Yes, we're going to have a look.
Where's the feed point on that?
Yeah, there's a, right there. Yeah, a couple of bare wires, pick up alligator clips off coax, and it'll work. It does work.
Is this the dipole you're passing around?
Yeah. Yep.
We'll get to you.
You
Okay.
get to see it.
I looked at dipoles, but I'm gonna check this one out, see if it's, I've made the simple dipoles where you have one hook to the ground and one hook to the hot side. You know, that would be what, an unbalanced dipole?
Yes. Yeah. Yeah, we're going to get to those.
And I've made, yeah, that's the easiest one for me to make, so.
So the half wavelength antenna is the basis of virtually every other antenna there is out there. The only exception is a loop antenna, which uses a full wavelength. I'm not going to really talk about that tonight because that's its own subject. It can go very long, so I'm going to try to keep this into sections so it's easy to understand. Your center feed point is 70 ohms. That's theoretical. And that means that if you were to place this antenna more than a half wavelength above the ground, flat, that's what the impedance is going to be. So if you were to run a line from the back of your transmitter to that feed point, you're going to have a little bit of mismatch. SWR maybe 1.7 to 1, perfectly acceptable for most modern transceivers. And I guess in this world of, we've got really poor propagation, and if you're interested in 40 or 80, that height for 40 meters, half wavelength is 66 feet. It's 120 for 80 or 75 meters. Most of us don't have that option. So when the antenna is lower to the ground, it has a lower impedance. Most inverted Vs set up 25, 30 feet in the air at the center will exhibit 50 ohms, which is a real good match for your transceiver.
So the closer to the ground you get, the lower the impedance.
lower it gets. And you can put them on the ground. I have literally put insulated dipoles on the ground, and they work. You can transmit through them, and you can hear really well with noise. So, but this has, when you've got it set up in a taller height, it picks up better across the wire, so it induces signal perpendicular. You tend to be a little deaf off its ends, so you get a pattern that looks like a figure 8 on the ground. And the lower that antenna gets to the ground, the more that figure 8 will go into a circle. It also just becomes a bubble. And if any of you ever heard the term NVIS, or near vertical incident skywave, take a dipole and put it low to the ground, and that's what you'll get. Because it bounces the signal up, straight up to the clouds, and back down again. And it's a functional antenna. So, I'm going to try something. Somebody tell me an HF band that's their favorite, and I can tell you how big the antenna is.
20 meters.
2200.
10, 65 feet roughly.
No, 20 meters is 32 feet.
32.
So, interestingly enough, I'm not a whiz at math. I'm really bad at figuring out math in my head.
We're not here.
The thing is that 468 divided by the frequency in megahertz, once you use that a few times, you start getting a picture of how big the antennas are going to be. So I mean, 40 meters is going to be 66, 120 to 135 for 80, 256 for 160. That's, you know, it's not our lowest hand band, but that's probably the lowest practical hand band, because we've got 630 and 2200 meters now. 2200 meters is a half a mile, roughly. 2.2 kilometers. No, it's more than that.
Let's pull out the old calculator.
Yeah, that's big.
It's
Two questions real quick.
600
I don't
hertz.
get too off topic. Are there actually radios that will tune up on those frequencies?
Yeah,
tune up or transmit.
Either.
either one.
I mean, you can take an FT950 and do the Marg mod, and you'll get. I'm pretty sure you'll get 600. I don't know if you'll get 2200, but whether the tuner will tune it is dependent on your antenna.
And then the second question for those Submariner fans out there, are these in the frequency ranges of like those long towed antennas that they pull behind the submarines?
2200 meters it's 137 kilohertz, but they actually do lower.
Okay.
They do in almost audible range. Well, it is for kids, I guess. If you can hear 15 kilohertz. I used to be able to hear old two-type TVs run. I can't hear them anymore. But
The VLF antenna.
Yeah.
That's what you're talking about.
Right.
And Lulu Lake, we used to get in the Jeep and drive around and do maintenance on it. It was 7 miles long.
yeah.
About a third of a mile is what it
And
is
that
on
was
the
a
2200.
land-based one. It wasn't so.
So the oddities is if you were to use the speed of light to figure half wavelength, you're going to come up with an antenna that's 5% longer than the actual wire. And the reason behind that is that the speed of light, you would call that a theoretical measurement, where wire has a tendency, it's, if you've heard of velocity factor in coax, well, wire has some too, and it slows it down by about 5%. So that's why our formula is 468 instead of 492 to measure wires. Now, that formula is, that I mentioned, is kind of what we would call rule of thumb, because most likely you're going to cut it, and then you're going to cut it again. And it's always better to cut a little long than a little short. So I have had the 468 formula, when you get the antenna pulled way up high, that was pretty darn close, but it always turned out to be just a little bit long in the real world. I'm sure if I could get to the altitudes I hear some of these hams talking about their towers, I probably would hit it right on, but I just don't have that. The lower it gets, an extreme would be if you laid a dipole on the ground, your resonant frequency is going to go way down, and that feed point impedance is going to go way down. You can still find a point somewhere where you can feed it, but that you'll have to impedance match it. But you might say if you had a 40-meter antenna and you just laid it in the grass, and it's insulated so it didn't touch the earth, that it's going to be down in the top, almost the top end of 8. That's how much it will slow. So, I think honestly if you did that on the beach it wouldn't work because of the conductivity of the soil. Our conductivity isn't real good here. So the actual ground appears to be several feet under the surface. Rocks, clay, you name it. And again, your distortion of the pattern means that the lower it gets to the ground, the more circular it is. The less that you see the perpendicular to the wire effect, and you get more of the upper bandwidth. Something that is important about the dipole, if you cut a dipole for 40 meters, you will also find that you can use it on 15 meters. that means that it also becomes resonant at 3 times the frequency. The only problem with that is it's no longer a donut shape. It looks more like if the wires going this way, they go this way and this way. So you have a wire that works better off the ends than it does off this side. So you can use it. It's going to make your transmitter happy, but it also will, you won't get an expected direction file. So, I don't know if I'm a real fan of Marconi or not, honestly, because he tried to claim he invented radio, and it was actually Tesla who did it. But he did invent this. And what Marconi did was he took the dipole, this wire that has a center insulator, he turned it on its top, and he used the ground as the other half. So the expectation there is you got good enough conductivity in the soil that you stick a rod in and then a vertical. That's not going to work here in the Ozarks, probably anyway. You are going to be creating a artificial ground with ground radius. Now I've seen, this is where, and I've been warned about this, you will always find somebody that'll yell, "That's rubbish," when it comes to the number of radials that you need. I've got 8 under a vertical at home, and the only study I saw said that when you get to 8, you can just keep adding them, and you start getting percentage points, partial percentage points of a dB. And I don't know, you talk to some ham, he's like, "Oh, you got to have 128 radials, or it won't work." I've got 8. I can hear South Africa at night. I'm pretty happy. I may put in 10. But wire's expensive, and it hurts to dig. So, you know, this is one of those things. The ideal ground plane is if y'all could get a mesh of small copper and lay it in a circle around the bottom of your antenna. That would create an artificial ground to make the monopole antenna work.
You mean you're actually burying this in the soil then?
Oh yeah.
Or just laying it on top and let the grass grow over it.
That's, yeah, you can lay a mesh. I've seen enough different experiments where people have laid down strips of mesh and then it just grew through the grass. Or somebody that soldered together a whole circle. It's an incredible antenna. It's like having 1,000,000 radios. It's just all conductive. So, you know.
You know Carl, I remember when he worked at welding, if they had the electrodes that went bad, he'd bring them home and made radials for his antenna, and I remember telling the guy he had 93 radials in the back of the car.
You probably would have lost about 0.2 dB if you removed 2/3 of those.
Right.
See, those radials need to be a quarter wave at least long too.
There's some experimentation that says otherwise. I built mine at 50%, and that's so I got a 30-foot, 32-foot, 33-foot long vertical. I put them in at 16 feet. There are some that says 40 is 40%, so I could shorten them up even a little bit more. I'm going to say on that one, your mileage may vary. Because I went through the trouble of putting full quarter wavelength radials down, and these 16s were working just as good, as opposed to 32 feet. So I think honestly, if you've got some wire in the ground that's at least a 20 to 30% of your vertical, you're going to have something that works. Now, the reason why I'm up here talking about it is I want to make it easy. I want people to put up their own antennas. If you've got a chunk of a fence top you've sawed off to about 16 feet, and you've got a couple of radial wires laying in the grass, and you hooked up coax, you've got a pretty good 20-meter antenna. you might just get the elusive DX with that. So when some of us say, oh, you gotta go and, you know, it has to be this or that, there's always exceptions.
Well, there's nothing absolute. I mean, it has to do with the soil conductivity, and the impedance will change.
Right. I was, my first antenna, one of the first, was a dipole for 10 years. I was a Tech Plus. They didn't call it that, I was just Tech. I worked Australia on an antenna no higher than my forehead. I've got to say that a lot of it was his station. He had a much bigger gain than I had, but he heard me. 100 watts with an antenna that was almost in the grass. So I don't want to discourage folks by saying, oh boy, you can't put up an antenna. Yeah, do it. Just put it up. If it matches to your transfer, find out what you get. You might have a great time. So.
And if I'm not mistaken, if I'm understanding you right, this is basically the antenna we had at 366 on the air, right?
Exactly. And a guns and radio.
Yeah, and guns and radio. So if you want to, this can be a portable antenna.
Yeah. Yeah. I used military aluminum, the 4-footers, and I rigged up so that I can slide them up from the bottom. Because if you've got 8 of those together, it's 32 feet long. It's a pain to lift it up from the side. So pushing them up from the center is much easier.
It works great.
How do you get that back to 50 ohms?
There is a matching device, and I've worked with this on a couple of antennas now. I'm really happy. It's called a hairpin match. And what it is, it's basically a coil that goes between your radial field and the bottom of the antenna. And
Does that go on the shield side then?
it goes from,
Or the center?
well, the shield side goes to the radials. You have a coil, center conductor connects to the top of the coil, and then your antenna goes up from there. So what you gain in this is this acts like a shunt resistance, and it increases the resistance of what you get on a monopole antenna. So it's no surprise or secret 35 ohms is roughly half of a dipole. Well, you've removed half that dipole and you've got the ground there, so it's reduced it by that much. Well, when you add the hairpin match, it will make it closer to 50 ohms. Now, if you connect a dipole to this, or I mean a piece of coax to this, center conductor to the upright, it'll work. Again, it's about 1.6, 1.71. And there's a lot of commercial verticals that's all they do. They don't put any matching at the base. So it can be done simply. Get you some old aluminum porch railing. That's what mine is. You can buy aluminum tubing, obviously, that goes together. I don't know if any of you have seen DX Commander on YouTube. He sells fiberglass telescoping 10-meter poles. They're perfect for 40. You just hook a little tiny wire at the top, push them up, and you put some radios down on the ground, and you've got an antenna.
One thing that might be good to mention too is, you asked the question of whether it's connected to the shield and then to the, the center conductor or whatever. One of the hard concepts to start to understand and develop in your mind when you get into this is, it sounds off the top like you're going to short out the shielding in the center conductor. And one thing to get in your mind is just because something may be shorted from a DC perspective does not necessarily mean that it's shorted for an AC wave to go through, work through the matching network, and then radiate out the antenna system. So you technically, from a DC perspective, are shorting out the center conductor, which is the radiator, the vertical part of it, and then the shielding, which is your ground plane of it. But what you're doing by putting that coil in there is you're putting an inductor in there. So it works with the voltage in the wave as it goes through there to add inductance to the antenna, which if you take a multimeter is going to be shorted, but from an AC perspective, which all the waves that go through the antenna are AC. So it's hard to get wrapped around in that because you think, well, you gonna short the antenna out, but
Yeah,
that's,
that's what I was kinda.
yeah, because if you take any old balun, it's like a dual core balun, it's all shorted inside from a DC perspective.
Roger.
I had a similar thought about that short, but with the length of the coil and the frequency you're using, make a difference on the characteristic of that, how resonant the antenna is, with,
Yeah.
you know, and the length of the coil.
Yeah,
Yes.
it's a precise
Yes, it
thing,
does.
actually.
Okay, thank you.
Initially,
Because it
when I
sounds-
built the portable antenna, when I tested for resonance, I was at 7.4 megahertz. When I added the matching coil at the base for the hairpin match, it moved it down to about 72. And it also made that bandwidth of the antenna broader, so it covers the whole entire band at like 1.2.
What should the reactance to the coil be like?
You know, I don't have a way to tell you for sure what it is, but I will tell you that it's 2 inches in diameter and about 10 turns. And it works on 40 and it works on 20. So I've tested both. So
So is it actually just a balun then?
it's a matching device,
It's a matching device.
okay?
I
So,
was gonna say like on the J-pole, that's a perfect example of a dead short,
yes,
right? If you look at the coax and the, you know, the shield and the center conductor, just look at the size of the U, which is
right,
completely
right.
shorted out, so.
So the interesting part is in this talk, I'm kind of concentrating on HF antennas, but there is actually an HFJ pole. And it basically is a length of twin lead feed line with one half wavelength or 0.64 of a wavelength antenna connected to it. And so that's fed generally at the base, at the bottom, where a 2-meter J pole shorted, you feed it from that. It's called a Zeppelin antenna. And it wasn't because they loved Count Zeppelin, it was they put it on Zeppelin. Okay, so this explains the basics. I mean, when you hook up a piece of coax, got a piece of coax right here. The red one goes to the center conductor. Green one goes to ground. Get this out here. So they just connect. Just here and here.
Give me one.
So they just connect right in the middle. Now, it's as simple as that. That is an antenna, and it works. I have done this more times, honestly, than I could count, and had great SWR, and sometimes I had RF on the coax that'll make you want to throw the microphone.
Common though.
Yes. So, if you're running a higher power level, my comment here, it needs to have a choke to stop sheath currents. And you asked about this before we started. The reason why is a dipole, where let's just say that the north side has got the hot leg that's coming from the transmitter center conductor. The south side is connected to the ground. RF kind of doesn't understand direction. So what it does, instead of necessarily following the south path, it'll follow the coax. Now coax is this funny thing. The signals you send through it, it's on the outer side of the conductor, it's on the inner side of the outer conductor, or on the inside. This current comes back on the outside of the sheath. So it could be going on the same wire, it can be going this way on the inside and this way on the outside. So to counteract that, you put a choke on the outer conductor at the feed point. He asked about a coil. You can turn coax into a coil, which becomes an RF choke. It stops the RF at that point.
Dirty balun.
You can use ferrites, and that it's just metal. It's a powdered iron, and it's compressed into a shape that fits around your coax. You can get snap-on versions. They make them in toroidal shape where you just put your coax through it. You can also get fancy and build a common mode choke out of a ferrite, which what its purpose in life is. It lets currents travel this way and this way simultaneously, but if they come in two directions or one direction on two wires, they've got a real high impedance. So this might be your Google study is look up a common mode choke and see what it is. They're in everything. If we took apart an old monitor right now, you'd find one in it. It's just there to prevent common mode interference or common mode RF on coax, same thing. And yes, you will throw your microphone if you don't deal with it.
Well, that's a picture of a center-fed dipole, but when we went down to Branson, or down to the lake that time for the Route 66, okay, you made an off-center dipole.
Yep.
And is there an easy answer why it has a broader range than a center-fed?
Yes. The answer is that when you off-center fed, number one, you've changed the impedance. So the center point of that dipole is 70 ohms approximately. When you go to the off-center fed is generally half the distance between one end and the center feed point. You get into a part where the impedance is higher. So the feed point impedance on that off-center fed still works like a half-wave dipole, but it's like 200 to 400 ohms. So you have to use a balun, which is a transformer that takes 50 and turns it up to 200 to 400. I know you guys have seen the 4-to-1 baluns. MFJ sells a ton of them. Everybody has those. That's what they're for. They're for that off-center fed. It also will, and I'm not sure why, because it goes 4-to-1 goes to 200 ohms, but guys will take and they'll hit twin lead, 450 ohm twin lead. So there is a bit of a mismatch on that, but it seems to work better than just coax.
Well, I got that antenna at the house,
Yeah.
and I tried using it on my radio with my auto tuner, and it wouldn't tune up for diddly.
Right.
So I added 50 or 60 feet of that old twin lead on there. Sucker loads up perfect.
Right. So this actually is a future subject where you're talking about a multi-banded antenna. What happens is when you off-center feed them, you get more than one point where the impedance to drive the antenna is closer to what a transmitter wants than a regular dipole. So you're gonna hear all kinds of different terms out there. End-fed halfway, that's another one. Now that one is related to this dipole. Eliminate the center feed and feed it from one end. You have 2,000 ohms or so of impedance, and it will work as a half-wave dipole. Back to the J-pole theory, that's what they are. It's a half-wave antenna with a quarter-wave meshing section of feed. Same thing as a dipole, it's just fed from one end instead of another. So, and the J-pole or the Zeppelin antenna, you need to deal with those RF currents that come back on your coax. This is for you. A balun is a matching device that goes from balanced feed to unbalanced, such as coax to twin lead. It is a transformer. It's not anything but a transformer. You will always find wires wrapped around something or wires in the air that transform impedance. The un is the same thing. It is a coax in to another coax out, and it transforms impedance.
So then, like an example of that, would that be like your one-to-one balance?
No, because that's incorrectly determined. The one-to-one balance is a common mode choke.
Is a combination.
Now, something that the in-fed halfway people have been doing is they use the coax as a counterpoise, because you kind of get some built-up current that needs to go somewhere. So what they do is they put a choke at a quarter wavelength on the coax. That becomes a radial or a counterpoise.
Those off-center fed Wyndhams, you'll find that more than anything. They're sold that way, where they have you hang the antenna in the air, it's an off-center fed dipole, but then you have a piece of coax that comes with it that you'll notice at the bottom is fairly stiff. It's got a bunch of ferrite cores on there, and they actually use that piece of coax as a vertical radiator part of the antenna, so it becomes the counterpoise for the antenna itself, which a lot of times is why off-center feds can, one, be better multi-banded antennas, but two, oftentimes come out as a circular polarization. So,
What's a counterpoise?
Counterpoise is a place where RF that needs to go to ground can go. Okay, so doesn't necessarily connect to the earth, but it's dissipated through that piece of wire.
You can look at it like the other half of the antenna.
It
Yeah.
could be looked at. Yeah.
Is that the radios that come out then? Is that a
It can be, yes. Yes. Now, again, some of these terms are kind of all-inclusive, because I've heard people call radios counterpoise. To me, they're the earth. They're the RF earth. And that kind of gets into the argument of grounding, where you've got three types of grounds. You've got that protects you from short circuits, the return for the electric current that comes to your house, and the earth where RF goes to die. So those are the three. That's another talk. That'll be another meeting, probably.
So is that the same thing as a ground plane?
Same thing. Ground planes, counterpoise.
I give you an example. I run a radio on a boat. It's all fiberglass. There's no ground plane per se or anything. Counterpoise into the lake. Use the lake.
I know on the airplanes, when we put radios into the airplanes, and we were dealing with a fiberglass airplane, that was a pain, because then we had to put a mesh under the skin of the fiberglass, or the radio wouldn't work.
Right, right. And on bigger boats, they put a copper plate in to the fiberglass so that it doesn't touch the water, but it is capacitively touching the water. And it works exceptionally well on salt water. I don't know if you did salt water.
Actually, I never ever put a radio out. I only live a block off the ocean. That's plenty of salt.
Yeah.
In fact, the government actually has towers out in the salt marshes. Whatever they were doing, you know.
Make a great ground.
But that was where the shield always hooks to then.
Right.
Okay.
So in this example, if it transforms impedance, or it converts from coax, which is a grounded shield, to two wires that are balanced and feeding, that's a balun. Okay. And to me, a balun is 300 ohm to 75 on the back of your old TV set that wasn't cable ready. So
that little transformer is actually a balun then?
yes,
Okay.
that's actually a balun, because it converts balanced on balance.
Okay.
An old cable guy, spent a lot of time around that. So, you can feed your vertical directly. It works very well. We've kind of covered the thought about radials and having a ground field or a radial field to make up an artificial ground, and the hairpin. This does not generally put RF on the coax unless you've got something you've got a loose connection to your radials on the sheath, it'll talk right back to your hand on that metal part of your knife, and you'll have a mark there from it.
You mean
I know this.
You mean electric? It'll burn you electrically?
Oh yeah,
RF burn.
it hurts because you don't know it's happening until it's too late. Oh.
I mean, it's like microwave then.
Yeah,
Kind
it
of.
is like cooking you. Just
Oh.
takes longer on HF.
Wow.
So generally,
Yeah.
like if you've got a problem with, and you're getting RF coming back on your coax on a vertical that's got a ground connection, you've got a problem in your ground because the RF should go there. Right?
When you were talking about that coil, was that a loading coil you were talking about on the bottom of your?
It looks like one. Now,
So where did you feed that? At the bottom of the coil, you said?
the bottom goes to the ground,
Okay.
so your radials are here. The bottom of the coil's here, goes like this to the top. That's where your center conductor goes, and this is where the antenna goes.
Yeah, it's a connection between the center conductor and the coax and the shield of the coax. It's an inductor between that. A loading coil, a lot of times when people use that, like in mobile antennas, what they're doing is they're putting a coil inside the radiator that's making the antenna electrically longer, even though it's not making the antenna 50 foot high on your vehicle. So that,
It's a loading coil, usually a series.
yeah, no, it's not a loading coil. It's a
An actual
matching.
loading coil would go above the
So to speak, something that's probably sacrilege around here, but something that I might understand, which was CD.
Hey, I still have a CB.
Okay. So
Good heavens.
on the old antenna trunk, that was just, the normal CB was 102-inch width.
Mhm.
And then the short ones had the coil on the bottom.
That's the loading coil.
So all that was just enough wire to make that 102 inches, basically.
Yep, and just make the whole thing shorter.
But it's not the wire length. Yes, the inductance. It's not they add enough wire to make it 102 inches.
Oh,
Yeah.
I thought that's what it was.
Well, it makes it electrically 102
Makes
inches
it
long.
electrically
It doesn't necessarily mean if you
Right.
undo that it's 102, but
So-
from an electrical standpoint, it's
So to
102.
give you an example, and this goes out of what we're talking about, but it's VHF, on a 2-meter beam that has a driven element that should be 1/2 wavelength, its center feed point impedance is low on the order of 10 ohms. So what you do, you split it, and there's a piece of wire about this tall and about that wide that goes down, it grounds to the boom and comes back to the wire. That's a hairpin match. That makes the two about 40 to 50 ohms.
Well, that went right over the top, but I'll think.
You could vary that, you can make a 2-meter beam with a 50 ohm impedance by moving the spacing on the driven element.
Right, designed for a specific front to back ratio. You don't want to move that. So you match it in your notes, put down hairpin match. There are literally thousands of documents explaining what it is.
It's like when we did the tape measure antenna.
Exactly.
We used 18 gauge and a 12 gauge wire, basically, and 5 inches to make the loop, and that is the hairpin match.
Yep. And that brings that low impedance up to a little more manageable.
So yours is just a coil because it needs the length.
Right.
And you don't want a hairpin sticking out 6 feet.
Right. I could technically put it out
Right.
and back, but it's hard to mow around.
It's all the radials and ground you mow.
Yeah, they're buried in there.
I'm done mowing for the year. The belt went, secondary belt on my mower went out. I gotta get it. By the time I get it, the grass will be dormant, so it doesn't matter.
There you go.
By next year,
Keep thinking that.
they're gonna be under the grass.
Actually, they don't, because I had coax in the ground, and I laid it on the ground, and more or less, about a month, 2 months later, the grass had covered it up.
I have worked for Southwest Minnesota Cable, and they buried a lot of cable. And in the process of burying the cable, they went over some power lines that were supposed to be buried 6 inches in the ground. And literally someone to do it, go stand and watch
Another term, hairpin, if you want to put radials out in your lawn and don't want to bury them all, use a little clip, like a horseshoe-shaped wire. They make landscape wire that does this, and you just pin it down to the ground. Make sure it's on the ground, and in time, the grass will fill it in. You won't hit it with your mower. Even at first, you won't hit it because you should be mowing between 3.5 and 4 inches.
Right.
You ready?
That means I'd have to mow twice as often. Ain't gonna
Okay.
happen.
I put electric
So
fence
the
radios
mark
down.
of
I
the
didn't bury them.
resonant antenna
I
is
used electric fence
efficient.
wire. I didn't
And
bury them. I just mow over
The,
them.
the
Oh,
interesting
yeah.
part about the half wavelength antenna is it doesn't matter where you apply energy to it, it travels from the RF wave travels from one end to the other and back again. It's not too short or too long, which makes it an efficient radiator of radio energy. That's the goal. That's what we're looking to do. 100 watts equals the maximum amount of energy going into the air. So when you use an SWR meter on your radio, you are not measuring that. You're only measuring what the antenna is reflecting back towards the transmitter. So I give you a really great example. Half wave, end-fed half wave uses a transformer that is 49 to 1. So what that is for every one turn around the ferrite, there are 7 turns around to the secondary, which means that it steps it from 50 to somewhere around 2,000. It's approximate. You know, when you get into the high ohmic values, it can be off a little bit. That's cool. It's not going to be a problem, but it represents a pretty good match. A half-wave antenna is still a half-wave antenna. When it's cut to the right length, it's the most efficient radiator. So it's resonant. It tunes. But when you are using, you know, honestly, I think the whole term behind VSWR could be a whole, Dave Castler did a whole video about it, explaining what takes place on your coax. Suffice it to say is if you're feeding 75, 80 ohms on a dipole and you've got 300 feet of cable, when you read it, it's going to read pretty close to 50 ohms. And that antenna ain't working the way it should be. Because the reflected energy that's coming back from the antenna is attenuated and you don't see it underneath.
Maybe a whole other subject, but I had read or heard or something that I thought the 5/8 wave antenna was supposed to be a lot better than a half wave
I guess it kind of depends on who you talk to.
antenna.
Okay. Super penetrator.
Yeah.
CB antenna,
Yeah.
10 meters. They are one of the more efficient vertical antennas. And it's
5/8 wave.
yeah, it's 0.64 of a wavelength. The match to those is not 50 ohms. If you took 5/8 of the 40 meter antenna, it's not 50 ohms. It's more like, I don't know, 80, 90. It's very high because you're starting to get into that long. So that antenna I had up where you've got a center feed point, there's a graphic you go on. If you go on Wikipedia and look at the dipole, you're going to see a graphic that shows it goes like this. It's just a big dome shape. And this represents current. The current at the center is very high, real tall, and now at the ends it's almost nothing. When you go past half, it starts to the other direction. So 5/8 actually hits partially past. And you can calculate it, and the math is incredible. I did not one of those things I'm going to try to put on you today, but you can calculate what the impedance is. You match that impedance with a device, a coil, a capacitor. We've got tuners out there, the L network, pi network tuners that will match that, and it will represent 50 ohms to your transceiver, and it will match the antenna's impedance, and it will be efficient. But the half wave, actually, I'm going to say it's slightly more efficient.
So it's going to, the half-wave will actually give you a better gain then?
You get into a very complicated thing. Antennas by themselves are an entire industry of engineering that amateur radio only touches as much as you want it to touch your amateur radio career. The big thing is that when you're talking about SWR, just because you have a good SWR does not mean you have a resonant antenna. Doesn't mean that that antenna is working the best it can. You can make an antenna SWR super low by just using a tuner, just doing whatever you need to. Lengths of coax cause the reflected power to attenuate, so you don't even know that your antenna is not good, which is why you always measure the SWR at the base of the antenna, not at your radio. But the having a good SWR does not mean having a perfectly resonant antenna. The resonance of the antenna is determined by the inductance and capacitance. So when they equal each other out, the antenna becomes purely resistive, and that's when the antenna at the frequency that you're running becomes resonant in its most efficient state. That means it's going to radiate all the power that it's given. But the SWR may be 2 to 1 because the feed point impedance of that antenna happens to be 100 ohms. So you use both. You make the antenna resonant for the frequencies that you want, but then you match the feed point impedance to be something that your radio is happy with. You do both. It's those two things in combination to make an efficient antenna.
So if you were building an antenna and you had the nice MFJ 259 analyzer, so to speak.
Okay, a lot of people have them.
Huh?
A lot of people have them. It's a good analyzer.
I'm thinking about wanting to get one of these. But anyway, so do you measure, to determine how efficient your antenna is, do you measure the antenna with that before you put a balun or anything in then?
So
To see how efficient it is?
First, is anybody studying for exercise?
Let me see, let me do the question here. Let's do this question later,
Okay.
because we're past time.
Yes.
Okay.
Yeah, I don't want to drag it out too long.
Well,
No.
they'll be more than happy to answer your question, it's just that you've gone over probably half the people's heads in here. And
Wait,
don't
see,
really-
we went into the next slide here, so.
this is a good opportunity. Tech Days. Tech Days, we have all day to go over everything you want.
Okay.
We got a big old
Well, I didn't
marker
mean to
board.
get in, I don't,
You're asking questions. That's the thing that people often don't do, is they don't
Right.
ask the questions. That's exactly what we want. The problem with it is antennas is probably the biggest conversation you can get into.
Okay.
So I want to kind of cap this and conclude with, we're not going to be able to generally afford, there are some exceptions, the ideal antenna. And I can remember hearing them talk about, the dipole has to be a half wavelength on the ground, or it's just not going to work. That's not true. You can use small wire with soda bottle caps as insulators. I use telephone wire, the drop wire that the guys from the telephone company was dropping in my driveway because I said, hey, I'm tired of you parking in my driveway. What are you going to do about it? They gave me wire. It was great. So you're going to build a vertical out of steel pipe. Who steel pipe, that's not conductive. Yeah, it is. It's very conductive. It works great. It might not work as great as the purists might think, but it works. So the idea here is that don't let what this is stop you from building your own antenna. And honestly, I kind of knew when I started, I can plant a seed. You guys gotta take it from here. So you've heard the terms. Google can be your best friend. You do have numbers. That's what contact us is for. So, yeah. Any other Question?